In the last section of the book, we did some very basic integrals, calculated some very basic anti-derivatives. They were, the rules that we derived were just derivative formulas in reverse. All the basic derivative formulas that you're supposed to know, you just read them in reverse, and those give you the integral formulas. The two complicated ones were substitution, which is the chain rule in reverse, and integration by parts, which is the product rule in reverse. In this section, we're going to do some special trig integrals, a few that are just special and involve trigonometric functions, and they come up from time to time, and some trig identities help you integrate them, and then some functions that don't look like they have anything to do with trig at first, but the way you solve the integrals, the way you find an antiderivative, is you make what's called a trigonometric substitution, and you change it into an integral that does involve trig functions, and then once again kind of trig identities help you integrate the functions. So let's just start. There's some special ones. So how do you integrate the tangent of theta with respect to theta? Well, this one is very simple, but still, it's not just some differentiation formula that you have memorized in reverse. You write tan of theta as sine theta over cosine of theta. And then it should, if you stare at this not too long, it should occur to you that, oh, a substitution would be nice here. If you let u be the cosine of theta, then du is the derivative of cosine of theta, so that's minus the sine of theta times d theta. And we have a sine theta d theta, so this part would be u. There's sine theta d theta. We don't have this minus sign. That's easy to fix. So write this as minus du equals sine theta d theta. And this integral becomes, so the 1 over cosine of u is just 1 over u. So that's 1 over cosine of theta is 1 over u. And then you're left with times sine of theta d theta, but that's times a minus du. You're not subtracting du, it's times a negative du. You pull out the minus sign, you get minus, then the integral of 1 over u du, that's the natural log, the absolute value of u, plus a constant, and then you put back in that u is the cosine of theta. So you get minus the natural log of the absolute value of cosine of theta, plus a constant. Using properties of logs, you could take this minus sign and bring it inside and have 1 over cosine of theta inside the absolute value signs. That's the same as secant. So if you'd prefer, you can write this as the natural log of the absolute value of secant theta plus c. All right, so that's our first example of a nice trig integral. We didn't have to use much. Let's look at one that's significantly more complicated. It might not seem like it should be any worse because there we had the integral of tan theta, now we have the integral of secant theta. How much harder can it be? Significantly harder. And since I know the answer, I could just give you the answer and then we could verify that it's correct by differentiating it and making sure we have secant theta, that we get secant of theta. It's a little unsatisfying. We'd like to kind of have an idea of how someone came up with this result. So I think the easiest way to see this is you look at the derivatives of tangent and secant. So the derivative of tan theta, you're supposed to know it's secant squared theta. And the derivative of secant theta, you're supposed to know it's secant theta times tan theta. And if you combine these, what that means is that if you take secant theta plus tan theta prime, so take the derivative of that sum, you get secant theta tan theta plus the derivative of tangent is secant squared. And you can factor secant theta out of both places. You get secant theta times tan theta plus secant theta. Who cares? Why do we care about this? Well, this part in parentheses right here, tan theta plus secant theta, is the same thing that we started with. So what does this line show? It shows what we just showed, is that if u is secant theta plus tan theta, then what? Then its derivative, that means with respect to theta, so then du d theta equals secant theta times u, or I'll write u times secant of theta, just to save myself some parentheses. You get this. Well, what does this mean? Well, if you put the u over here and the d theta over there and insert integral signs, what it tells you is that, without the integral signs, it says 1 over u du is secant theta d theta. And so this integral, with this substitution, becomes 1 over u du. That's the natural log of the absolute value of u plus a constant, and that's the natural log of the absolute value of secant theta plus tan theta plus a constant. So that's the integral of secant of theta. Should you memorize this? It depends on what your instructor says, but typically this is the kind of thing you'd look up in a table. Most people do not memorize this one. The integral of tan theta is so easy, it's barely worth, you shouldn't memorize it exactly, but you should remember that if you just write out tan theta in terms of sine and cosine, it's an easy substitution. All right, what's a third integral that we want to do? Well, secant cubed. It's kind of strange, but this integral does pop up over and over again in calculus problems. Maybe after you've done a trig substitution. And it's, you find this integral by integrating by parts, but and you have to use the formula for the integral of secant, but it's an interesting integral. So we would like to integrate secant cubed theta d theta. It may be hard to believe this comes up over and over again, but it does. All right, how could you possibly integrate this? Well, let's split off a secant squared. So this is secant theta times secant squared theta d theta. Why do that? Because secant squared is tan squared plus 1, and maybe some trig identity will give us something. You know, you try to do something. So you use the trig identity, kind of our second most fundamental one. The first one, of course, is sine squared plus cosine squared equals 1. But the second most fundamental one is tan squared plus 1 is secant squared. So secant squared is tan squared plus 1, or 1 plus tan squared theta d theta. Now you can multiply this out and split up the sum of integrals, and you get the integral of secant theta d theta, and then plus the integral of secant theta tan squared theta d theta. The integral of secant theta is what we just did. So what we get is that this part is the natural log of the absolute value of secant theta plus tan theta. But then how do you integrate this part? Well, it's not so obvious. But you integrate it by parts. So you take tan theta, one of the tan thetas, and I'm going to put it over here, and then I'm going to kind of group the secant theta tan theta with the d theta, and I'm going to integrate by parts, and this is going to be my u, and all of this then will be dv. And the reason I split it up this way is because whatever you pick for dv, you have to be able to integrate to produce v, and we know that the integral of secant theta tan theta is just secant of theta. Right? The derivative of secant is secant times tangent. So the integral of secant times tangent is just secant. So I'm going to make this choice and integrate by parts. What happens when you integrate this by parts? Well, you've got u is tan theta, dv is secant theta tan theta d theta. What does this mean? So du, you will need du. It's the derivative of tan theta times d theta. The derivative of tan theta is secant squared theta. So we get secant squared theta d theta for du. And v is the integral of dv. And as I said, the integral of this is just secant of theta. You could put in plus a constant, but remember, when we're integrating by parts, we don't need the most general thing. We need one antiderivative, so we don't usually bother putting on the plus c. Okay, so what does this tell us? So we've got the natural log, the absolute value of secant theta plus tan theta. And then you've got this, which is the integral of u times v. Integration by parts says that that should equal u times v minus the integral of v du. Okay, well what is this? U times v is tan theta times secant theta. And just to keep my order kind of the same, I'm going to put in secant theta times tan theta. I'm going to reverse things just so secant comes first, just to be kind of consistent. Natural log, the absolute value of secant theta plus tan theta. U times v, tan theta times secant theta. I'm going to write secant theta times tan theta. And then minus the integral of v du. What is v du? It's this times this. That's secant cubed theta d theta. All right. So what happens? We integrate secant cubed theta d theta, and we get that it's the natural log, the absolute value of secant theta plus secant theta times tan theta minus the exact integral that we started with. But we looked at something like this before. This is fine, because now all we have to do is that appears with a minus sign. If you add this integral to both sides, you get 2 times the integral of secant cubed theta is this part, and you divide by 2. You have to put back in a plus c. That kind of vanishes because we had an indefinite integral on both sides. We could have had different constants, and we really should leave one over on the right. But this is what we do. So if you add this part to both sides, by both sides I mean here's one side and here's where we started. Add secant cubed, the integral of secant cubed theta d theta each place, and you get 2 times the integral of secant cubed theta d theta, and I guess I'll rearrange to write things in the order which they normally appear, equals secant theta times tan theta plus the natural log of the absolute value of secant theta plus tan theta plus a constant. You get this, and now you divide by 2. And just call c over 2 c again, since it has no meaning for us, really. This. And that's what you get. Should you memorize this formula? Absolutely not. Maybe you'll remember it without actually having to actively memorize it, but no. But it's the kind of thing you'd look up in a table, or the kind of thing you'd rederive as practice with integration by parts. But no, you shouldn't memorize this formula. All right, there are a couple more trig formulas that are useful. These are also the kinds of things that you look up. In fact, I might look them up to make sure that I don't mess up a minus sign. But these are iteration formulas, and what that means is you iterate these formulas. So you might use them multiple times in a row to actually finally get the answer. Iteration formulas. We want the integral of cosine raised to the nth power and the integral of sine raised to the nth power. where n is an integer. So n greater than or equal to 1, an integer. And the formulas, actually I'm not sure they're going to fit right here. Let me move this down a little bit. I'm going to write them from memory, and I'm going to double check that my memory is correct. Okay. Actually, maybe I'll just do them right the first time. The formulas are 1 over n cosine n minus 1 to theta sine of theta plus n minus 1 over n times the integral of cosine to the n minus 2. In fact, I wanted this to be greater than or equal to. This one. And then the one for sine, it looks like you just switch all the sines and cosines every place except you have an extra minus sign out in front here. So it's a minus 1 over n, a sine n minus 1 theta, cosine theta, plus n minus 1 over n times the integral of sine to the n minus 2 theta d theta. How do you use these iteration formulas? When n is 1, we already know how to integrate cosine, so you don't need to use it when n is 1. If n is 2 or bigger, then what happens? Like maybe n is 6. What happens? You apply this formula with n equals 6. It gives you this part plus, you need to know the integral of cosine raised to the 6 minus 2. So you need to know the integral of cosine squared. Oh, but you can get that from this formula again, because now you put in n equals 2. And you get this part with n equals 2 now. And then this part with n equals 0. Well, cosine to the 0, that's 1. And so the integral of the 1 d theta is just theta. If you start with something odd, like n cubed, cosine cubed, then again, after you get down to cosine, you put in n is 3. You get this part, and then you get cosine to the 1. But you know the integral cosine theta d theta is just sine of theta. So, right, these are iteration formulas. If n is big, they just tell you this answer in terms of what happens when n is too less. So you can eventually work your way down to where this is either 0 or 1, and you know how to integrate in both of those cases. So why are these iteration formulas true? Well, they're both integration by parts. I'm just going to do the top one. And the bottom one I can leave as an exercise for you, but they're exactly the same, really, in the steps that you do. All right. So let's do the cosine of n. All right, I said we're going to integrate by parts, so we need to split off some part that's going to be part of the dv. So I'm going to write cosine of n minus 1 to the theta, and then times the cosine of theta, d theta. And I'm going to let this be my u, and this be my dv. If you do that, then what you've got u is cosine to the n minus 1 of theta. dv is cosine of theta d theta. All right, v is always the integral of dv, so that's easy. And we don't need the plus c, so v will just be sine of theta. du, you have to be careful. This is cosine of theta raised to the n minus 1 power. And so it's the chain rule. You do the power rule first, so you get the n minus 1. You subtract 1 from the exponent, so you get an n minus 2. theta. But then by the chain rule, you have to multiply times the derivative of cosine of theta. Derivative of cosine of theta, you get a minus the sine of theta. And then there's still a d theta here. All right, so there's du. Of course, after we wrote it like this is the integral of u dv, and integration by parts says that this is uv minus the integral of v du. All right, so what does that give us? U times v. Well, we see part of what we're getting for the answer. Here's u, here's v. U times v, cosine n minus 1 theta times the sine of theta. There's u times v, minus the integral of v du. V is sine of theta. Times du. Du is this mess. So I'll just write all of that. So we get n minus 1 cosine raised to the n minus 2 theta minus sine of theta d theta. Okay, the n minus 1 is a constant. We can pull that out of the integral. The minus sign is a constant. I can put that there, so I'll get a minus, so a plus here, pull out an n minus 1. You get cosine to the n minus 1 of theta, sine of theta, plus n minus 1 times the integral of what's left. There's a cosine raised to the n minus 2 theta, and then there's sine times sine, so times sine squared theta, d theta. And this is where trig identities come in. We use the fundamental trig identity now and rewrite sine squared as 1 minus cosine squared. All right. All right. So what do you get? You get, I'm going to write what we started with, which is cosine of theta raised to the n d theta. And so far what we've shown is that this equals cosine to the n minus 1 of theta times the sine of theta plus n minus 1 times the integral of cosine to the n minus 2 of theta, and then times sine squared, but we write sine squared as 1 minus cosine squared of theta d theta. And now you multiply this out, and you see that one of the pieces we end up with is minus, we'll have a minus n minus 1 times cosine to the n minus 2 times cosine squared. The exponents add, we're back to cosine to the n. But we're going to do our trick where we add back and divide, so don't worry. So you get cosine to the n minus 1 theta, sine of theta. There's this part, the plus n minus 1 times this times 1 d theta. So plus n minus 1 times the cosine n minus 2 of theta d theta. And then this last part, which is minus n minus 1. So minus n minus 1 times this, but that's cosine n theta again. Cosine of theta to the n d theta. So what do we get? We get the integral of cosine of theta to the n d theta is this part plus this part minus n minus 1 times what we started with. So what do? We add this back to the beginning. So we add 1 times the integral to n minus 1 times the integral. You end up with n times the integral. So you end up with, after you add that to both sides, n times the integral of cosine n theta d theta equals this other part, cosine the n minus 1 theta sine theta plus n minus 1 times the integral of cosine raised to the n minus 2 theta d theta. We should put in a plus c that we lost when we removed the indefinite integral from that side. And then you divide both sides by n. Just divide, and you get the formula that I wrote on the board. Should you memorize this? Again, no. It's something you look up in a table or do on a calculator or on a computer, or that you rederive as an exercise. How long was that exercise? I don't know, 5 minutes, 10 minutes? It doesn't take long to rederive, but you have to know how to do it. And it's mainly integration by parts. So this is what you get. And the one for sine raised to the n of theta d theta, you do the same steps. All right. Those are some special trig integrals, which actually do come up often. They're not really basic. They really are the kinds of things that most people look up in tables, except maybe the integral of tangent, which is pretty easy. But there are integrals that don't look like they have much to do with trig that you make substitutions into and turn them into trig integrals. So this is an important enough technique that people give it a name. They just call it trig substitutions, trigonometric substitutions. So trig substitutions. And I just want to do 3 examples of this. So what's an example? So our first example of trig substitutions, which I guess, considering that we just did 4 other integral formulas, I guess I should number this 5, but I just won't number it anything. Here's an example of an integral you do by trig substitutions. You look at this integral, and you don't know how to do it, and you'd like to know how to do it. So what do you do? And what you think, or hopefully what you'll think after this anyway, is that, oh, if only I let x be a sine theta, then things would get better, because then the square root of a squared minus x squared would equal the square root of a squared minus a squared sine squared theta. And I didn't say it, but I meant it. I want, anytime I do write a in these examples, I mean that a is greater than 0. Why is that important right now? Well, because I can factor out an a squared from here and here. The square root of a squared is a, if a is positive. Actually greater than or equal to 0, but I'm assuming it's positive. So the square root of a squared is a. This leaves me with a times the square root of 1 minus sine squared theta. But 1 minus sine squared is cosine squared by the fundamental trig identity. And so we get the square root of cosine squared theta. Now, we'd like to say that this equals a cosine of theta, so that this integral becomes a lot nicer. So that this thing under the square root becomes a cosine of theta. dx would be easy. I didn't say it, but if x is, or I haven't said it before now, but if x is a sine theta, certainly dx is easy. dx would be a times cosine of theta d theta. And so this integral would become fairly easy. The integrand becomes a cosine of theta, dx becomes a cosine of theta d theta. So we have to integrate a squared cosine squared. You can either do that with a trig identity, or we can use the iteration formula that we just derived with n equals 2. Okay, fine. So what's the problem? Well, there are a couple of subtle problems here. I mean, one is that the square root of cosine squared is cosine if cosine is positive. Nothing about x equaling a sine theta means that cosine has to be positive. But we have a more fundamental problem. X is something that already exists in this integral. We don't get to let it be anything. We get to let theta be things. We can define new variables. We can define a new variable theta in terms of x, but we can't just say let x be a sine theta. So this is the kind of thing we want to get, but what is it that you really do if you're not letting x be a sine theta? What are you doing? Well, divide by a and take the inverse sign. We really want to let what you really do is let theta equal the inverse sine of x over a. Can we really do this? Yes, because we're looking at the square root of a squared minus x squared. So in particular, x squared has to be less than a squared. Otherwise, the thing under the square root would be negative, or less than or equal to a squared. That means that x has to be between plus and minus, between negative a and a. So x itself has to be between minus a and a, so that this quantity under the square root isn't negative, so that you can take a square root of it. But this means that x over a, remember a is positive, this means x over a is between minus 1 and 1, but that's the domain of the inverse sign. Right? It's the range of signs, so it's the domain of inverse sign, or those values between minus 1 and 1. So yes, for the x's, for a, like up here, and x's that we're allowed to use up here, this theta is defined. Theta is the inverse sine of x over a. And that does mean that x is a sine of theta. In fact, it tells us more than x equals a sine theta. So if this is true, yes, we can let theta be this, which implies this is true, which implies all of this. So I'll just go ahead and, to save space, I'll just write Now we know that you get this. No, we don't. I wanted to say one more thing down here. But inverse sine gives you back angles between minus pi over 2 and pi over 2. So theta being inverse sine of x over a doesn't just tell you this, it also tells you that theta is between minus pi over 2 and pi over 2. This is important. Why is this important? Because if theta is between minus pi over 2 and pi over 2, cosine of theta, if theta is between minus pi over 2 and pi over 2, is greater than or equal to 0, so that the square root of cosine squared theta is a cosine theta, because cosine theta is greater than or equal to 0. So we do get this. And we have that dx is a cosine theta d theta. Putting those together, this integral becomes, I want my iteration formula. There it is. So putting those together, what we get is that this is, as I said, it's the a cosine of theta times another a cosine of theta d theta. So this is a squared times the integral of cosine squared theta d theta. And then either you use a trig identity, so the double angle formula for cosine. If you solve for the cosine squared part, would tell you that cosine squared theta is 1 plus the cosine of 2 theta over 2. So we could use this trig identity to integrate this. But since we have our iteration formula on the board, we might as well use that with n equals 2. And we get a squared times, when n is 2, we get a half cosine to the 2 minus 1, so cosine of theta times the sine of theta, plus n is 2, so we get 1/2 plus 1/2. The integral of cosine to the 0 of theta, that's just the integral of 1 d theta. That just gives us a theta plus c. And then you put back in what all of these things are. Well, sine of theta would be x over a. Cosine of theta is the square root of a squared minus x squared over a. And theta itself is the inverse sine of x over a. So what we get is you get a squared. I might as well pull out a half from both places. A squared over 2 times. All right, cosine theta. Cosine theta divided by a. It's the square root of a squared minus x squared over a. Sine of theta. Sine of theta is x over a times x over a. Plus, I pulled out the half, plus theta. Theta is the inverse sine of x over a plus a constant. This is what you get. You can neaten this up quite a bit if you want. It's because here's an a squared in this denominator that would cancel with this. I'll put the x out in front, so you could write this more neatly as 1/2 x times the square root of a squared minus x squared, and then plus this remaining part, so plus an a squared over 2 times the inverse sine of x over a plus a constant. And that's what we get. It's not particularly easy. It's not particularly difficult once you think to do the trig substitution, and then you realize that you can use any of the trig, the other trig integrals that you know, and trig identities. All right, let's do another example that looks so similar that it's very surprising that the answer comes out to be so different. But I just want to change this minus sign to a plus sign. How much harder can that make it? And the answer is, well, it doesn't really make it harder, but it does make it essentially completely different. And it is a little surprising. If we were doing calculus with complex numbers, we could take our answer from that problem and make a substitution in this problem that basically replaces x by I, the square root of minus 1 times x, and we could derive the answer to this one from the answer from that one, except then we'd have to know how complex numbers work in inverse trig functions, and it wouldn't be clear that what we ended up with was a real function either. So we're not going to do that, but we could. Okay, so what would we like to do here? We've got a squared plus x squared, and what we want to use is that tan squared plus 1 is secant squared. So instead of saying x is a sine theta, we're going to say x is a tan theta, so that we get another a squared. We can pull out the a squared, and you get 1 plus tan squared. That's secant squared. So that's what we want to do. Of course, we don't get to let x be anything. We get to define theta. So once again, we say let theta be the inverse tangent of x over a. Okay. Now, what does that mean? It means that two things. So we know that x is a tan theta. You take tangent of both sides and multiply by a. X is a tan theta, but it also tells us that theta, inverse tangent, gives you back angles between minus pi over 2 and pi over 2. So it tells us that theta is between minus pi over 2 and pi over 2. Great. So what happens now? Well, x is a tan theta. So dx is a times the derivative of tangent, secant squared theta, d theta. We need to figure out what the square root of a squared plus x squared is. So we do that. The square root of a squared plus x squared equals the square root of a squared plus a squared tan squared. You factor out the square root of a squared. A is positive still, so that's just an a. And you get times the square root of 1 plus tan squared. But again, 1 plus tan squared is secant squared. So you get a times the square root of secant squared theta. Secant squared is 1 over cosine squared. Actually, it's 1 over cosine squared. Cosine is positive for theta between minus pi over 2 and pi over 2. So secant is positive. This secant of theta is positive because our theta is between minus pi over 2 and pi over 2. So the square root of something positive squared is just that thing. So we get a is secant theta. Right? The square root of something squared is really the absolute value of the quantity. So if the thing is greater than or equal to 0, yes, that's just the original thing, the secant theta. So what we get is the integrand, the square root of a squared plus x squared is a secant theta. Dx is a secant squared theta d theta. I assume you can see where this is headed now. It's headed to a big mess, but it's a mess that we can deal with because we're going to get the integral of secant cubed theta, which we just derived a few minutes ago. So if you put these things together, what you get is that you get a secant theta times a secant squared theta d theta. So you get an a squared secant cubed theta d theta. But we know the integral of secant cubed theta. I told you not to memorize it, but okay, I've got it memorized, or at least I remember it. Right now, it is secant theta times tan theta plus the natural log of the absolute value of secant theta plus tan theta over 2 plus a constant. It's this, but we want the answer back in terms of x and a. So secant theta and tan theta, these occurrences of secant theta and tan theta, you need to replace with x's and a stuff. This is not hard to do. So secant theta, so tan theta is x over a. That's easy. So maybe I'll write these somewhere. The two occurrences of tan theta get replaced by x over a. Secant theta is right here. Secant theta is the square root of a squared plus x squared divided by a. And you plug those two things in, here, 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 and here, and you get the answer in terms of x and a. I'm not going to do it. It's not, again, it's not a formula you should memorize. You should look it up in a table, or you should rederive it every time. It's not easy, but it's not too bad. Of course, you had to know the integral of secant cubed, which you either have to look up or redo. So it kind of piles up in badness, but that's what you do. All right. Let's do one more that is an important integral when we get to the next section on partial fractions, which is another kind of advanced integration technique. How do you integrate? So I still want a greater than 0, even though I just erased where it said that. So still a greater than 0. I would like to integrate a squared plus x squared raised to the nth power dx, where n is an integer greater than 1. So integer n greater than or equal to 1. Okay, you've got an a squared plus x squared. So after our last problem, you should suspect that you want to make the substitution, well, x equals a tan theta. But really, you let theta be, so you let theta equal the inverse tangent of x over a. This tells us more than that x is a tan theta. It once again tells us that theta is between pi over 2 and minus pi over 2, whether we need to use this later or not. And if x is a tan theta, then certainly dx is a secant squared theta d theta, just like it was a minute ago. And we don't have the square root of a squared plus x squared anymore, but we have a squared plus x squared. What was a squared plus x squared? A squared plus x squared is a squared plus x squared is a squared tan squared. You factor out an a squared. You get a squared times 1 plus tan squared. 1 plus tan squared is secant squared. So you get a squared secant squared theta. All right. So what does this integral become? This integral becomes, all right. So the dx is a secant squared theta. The a squared plus x squared is, so we get a squared plus x squared is a squared times secant squared theta. and this is all raised to the n, and then it's times dx, which is a secant squared theta d theta. All right, what does this give us? All right, so we have a squared to the n. That's a to the 2n in the denominator, but then you've multiplied by an a in the numerator, so that's a to the 2n minus 1 in the denominator, or what's the same thing, a to the 1 minus 2n. Right? This is a to the negative 2n times another a. So you get that. That's a constant. We can pull that out. But you still have to have the integral of what? You get 1 over secant to the 2n. So this is secant to the minus 2n plus 2. But secant is 1 over cosine. So this is, I'll write it, but you get secant. Let me write it as 1 over, because I think it'll look better. You get 1 over secant to the positive 2n minus 2. So you get this. But 1 over secant is cosine. So this is cosine to the 2n minus 2. So what we get the integral of 1 over a squared plus x squared to the n dx is a to the 1 minus 2n times the integral of cosine to the 2n minus 2 theta d theta. All right, this is what we get. But we have a cosine iteration formula that tells us how to integrate this. And that's how you do it. I mean, we get an iteration formula for this integral, which isn't terribly surprising. So let's see what it gives us. Let's see what happens when n is 1. When n is 1, we don't even have to use an iteration formula then. We get something that we already know, the integral of 1 over a squared plus x squared to the 1 dx. This better come out to be 1 over a inverse tangent of x over a. But we'll see. When n is 1, we get a to the 1 minus 2, so a to the minus 1. When n is 1, we get cosine raised to the 0 power. So that's 1. Integral of 1 d theta. So we get 1 over a times theta plus a constant, but theta was the inverse tangent of x over a. So we get 1 over a inverse tan of x over a. Well, that's good. That's what it's supposed to be. What else do we get? Well, let's just do when n equals 2, and then you can believe that you use the iteration formula after that. So when n equals 2, so we'd be looking at the integral of 1 over a squared plus x squared squared dx. Our formula says that you get a to the 1 minus 2 times 2, so a to the minus 3. So this should be a to the minus 3 times the integral of, we're letting n be 2, so cosine squared theta d theta. Now we just integrated cosine squared theta d theta a minute ago. Either use, as I said before, either you use the integration formula, or the iteration formula, or you use the trig identity. What you get, either way, is a to the minus 3 times, we get a 1/2 cosine theta sine theta plus a 1/2 of just theta plus a constant. All right, this is what we got. couple of minutes ago. And so what do? Now you replace the references to theta with references to x and a. And so you have to do something to make this look a little nicer. This becomes the inverse tangent of x over a, and you need cosine times sine in terms of x over a, or in terms of x and a. This is not particularly difficult. You get x equals a tan theta. The kind of the sneaky way of getting this is that tan theta is sine theta over cosine theta. So, so that if you multiplied by cosine, so we have x is this. If I multiply by cosine squared on both sides, I would get x cosine squared. I'm just trying to get what cosine theta sine theta is in terms of x and a without getting too ugly. Multiply by cosine squared, that would wipe out one of these and leave us with a cosine theta here, divide by a. So you get this. Well, how does that help? Well, cosine squared is 1 over secant squared, so what we're getting is sine theta cosine theta is x over a times 1 over secant squared theta. But secant squared is 1 plus tan squared, so this is 1 plus tan squared theta, but tan, well, I've erased it, but x over a is tan theta. Anyway, there are lots of ways you could get this. This is just one of them. So what we're getting is sine theta times cosine theta is x over a times 1 over 1 plus x over a squared. Okay. Plus, no. Okay. So you get that, you put this back in, and you get the answer. You put this in where you have sine theta and cosine theta. You put in theta as inverse tan of x over a, and you get the answer. All right. That's all I want to do in this section. It's a bunch of manipulations with trig functions and partial fractions and special things that just use trig identities over and over again. These, you shouldn't memorize any of these or many of them. It's, you should know that this is the kind of thing that you do. You should know that these integrals are in the table. You should know how to integrate by parts. You should think about trig substitutions and other problems, like when you have something that's not in the tables. Really, what you should get out of this section is the techniques, not so much memorizing what the answers are.